have that kind of processing and storage to be able to handle it. I mean, just for one example, 5 million smart meters in a city, that generates over 100 billion data points in a year if you read it 4 times a year. And some of this stuff is so time critical, like a phase measurement unit that is actually adjusting the smart grid. If you miss that by a couple of milliseconds, the grid collapses. I think our previous speaker mentioned you don't want that to happen. Anyway, there's a prediction that there's going to be 50 billion connected objects in 2020. We think that's low. We think it'll be closer to 100 billion. And that includes, RFIDs, smartphones, etc. Now, it's big and it's fast. If you kind of think of a continuum, there's huge amounts of data where we can get the data into one place and apply deep analytics. And that's where we have Big Insights, which is our program, which actually is the same lineage as our Watson computer, where we can make sense of huge amounts of data. At the other axis, where we have data coming at us real time, where we have to act on it either at millisecond or microsecond kind of levels, or something bad can happen, that's where we're doing System S, which is actually moving the analytics down into the system, where we're going to actually process it as it occurs. So instead of bringing it back and working with it in the shop, you don't really have time for that. So the combination of those things can actually be built into hybrid systems where the real-time data is influencing the mining that you're doing. We have several examples. Like in security, in New York City, we have done a piece of work with our Deep Insights products where we're actually integrating all of the crime information of the entire city of New York. Now, you'd be surprised how much that is. It's victims' data, it's crime data, it's geographic data, etc., and giving instant geographic insight to anyone who looks of any crime that occurred. Not only that, we're mining it for patterns, and we're anticipating crimes and anticipating public disorder in such a way that we can act on it up front. We're applying this in smart cities. Anybody who's ever driven to a city like Moscow, you probably don't like traffic either. But we're applying these smart insights into cities like Singapore. Our mathematical modeling, we've been able to apply instrumentation of where the cars are and not just observe traffic congestion. We're actually able to predict it 10, 20, or 40 minutes in advance and meter the number of cars that are going in there. And by doing that, we've been able to reduce congestion in those roads by 18%. And it's only by making information useful that's already on that path. We're also doing this with mining. All of the easy oil in the world, they say, has been found. But we're working with companies like Restoil, where we're digging down. We've got drills 8 kilometers down under the seabed. We're using data that comes from that drill bit, shipping it to our supercomputer center in Barcelona, where 1,000 processors in pretty not real time, but pretty close to real time, will give us an image of where to steer that bit. And that we're able to generate images that we can actually adaptively move and find that difficult to reach oil. Now, the last one that we talked about of Deep Insights is this Watson computer. I don't know if you know Watson, but I was told that there is a show like Jeopardy here, Durgai, something like that. Is that how it's said? Well, this is a really interesting juncture right now where we're getting to the era of smart computing. But let's talk a little bit about Watson. Watson is an amazing thing. So I grew up watching this show, Jeopardy. These are where the smartest people, I always wanted to be on the show, but I wasn't smart enough. The smartest people in the world got there and they tested their knowledge of politics, history, rock music, rhymes, everything. The idea to build a supercomputer that would run against the best in the industry was just an amazing idea. And it wasn't just a stunt. It's because many issues that we actually handle in the world have that kind of deep, complex behavior. Now, this was not a special search engine, and it wasn't a supercomputer per se. Watson is actually built out of 90 commercial Z-series machines, P-series machines. And I actually was the methodology engineer on the chip that's in there, so I'm very proud of it. All told, that's almost 3,000 Power 7 cores. And with that data, we've been able to optimize a piece of software that actually decomposes these very complicated questions proposes a bunch of different hypotheses, tests them on thousands of parallel processors, and then weighs the results and gives you confidence level. So it did a great job. We were so proud that when it won on Jeopardy. But what's really exciting is what's coming now. So after winning on Jeopardy, the company is really working on what the commercial value of this is. And the first one that we're doing is on medicine. And we're working with WellPoint Healthcare. I've been watching this for the last 3 months. They are now at a point where they can make 75% accurate diagnoses on about 75% of the questions. And only with about 3 months of tuning, this thing is actually being useful to medical doctors in diagnosing diseases of the eye. You know, many things, it's not going to invent new technologies or new healthcare things, but it will help a human and will allow you to interact. It will ask questions, and then it will pose questions that you would ask to a patient. Beyond healthcare, there are many things in business, whether it's inventory management, help desk kind of things, national security. It's going to be an amazing time to watch this. Now, in closing though, that Watson is really, it's not thinking, but it's learning. There was no way you could program all the answers to all the questions on Jeopardy. Believe me, I've tried. But what is actually happening is something, we're trying to approximate what a human does well. But if you think about it, it's a bad comparison. Watson took 85,000 watts, the guys that it barely beat, the humans in Jeopardy, their brains take about 20 watts. Watson had 20 tons of air conditioning equipment. Those humans were probably creating their electricity from beer and pretzels. So it's quite an amazing difference. What it says, though, is there's so much room for improvement. And our scientists in Almaden are looking at those biologically inspired devices. So if you look at a mammalian brain, it's not a sequential computer like a Watson or a Z series or a P series. It's a large number of connected nodes that have a huge number of interconnections between them. And it learns by strengthening the number of connections. Our researchers in Almaden have built the first synaptic computer that it's a relatively small cross-section. It has 100 neurons with about 1,000 connections. And over the next couple of years, we're going to bring that up by 3 orders of magnitude because of the microelectronics to nanoelectronics improvement. And then put those in large arrays. And somewhere around 2020, we'll have the same level of connectivity as the human brain. Will it think? Not the way we think. But will it learn? Oh yes, it will learn. I've already seen this chip already recognize handwriting without any training. So it's going to be an amazing time. So what's the next couple of years going to bring? Well, in our 100 years, we've started at the age of tabulating, simple machines that count. We have all grown up in the era of programmed computers, where you tell it what to do. What's going to be amazing is the era of smart computers, which learn on their own. And it's going to be just a fabulous time to be in the IT industry. So thank you very much. Enjoy the rest of the evening.